We will now use the concepts we developed in the first part of this lesson to solve problems. To begin with, let's recall some of the formulae we developed. Now, can you recall some of those formulae? Well, the first formula is the wave equation. Wave speed equal to frequency multiplied by the wavelength. I hope you remember the definition of wavelength. Can you give me one definition of wavelength? I give you three. Wavelength is the distance advanced by the wave in a time of one period. It is the distance between two nearest particles that are in the same phase of vibration. And for a transverse wave, it's the distance between two nearest or adjacent crests or two adjacent troughs. For a longitudinal wave, it will be the distance between two adjacent high pressure regions or two adjacent low pressure regions. Okay, what is the second formula that we looked at? The speed of transverse waves on a stretched string, V equal to square root of T over mu. T is the tension on the string, mu is the mass per unit length. Alright? The third formula we developed was for the energy. The energy transmitted along a string of length delta x is 1/2 mu a squared omega squared delta x. Mu is the mass per unit length. Tell me, how do you find the mass per unit length? If you know the mass of the string and you know its length, total mass divided by the length will be mass per unit length. If you know the mass per unit length and the length of the string, you see, mu times delta x is the mass of the string. A is the amplitude of vibration. What is the amplitude? Amplitude is the maximum displacement, and omega is the angular frequency, which is related to the frequency of vibration as omega equal to 2 pi f, or omega is 2 pi divided by the period. Alright, all these you must be familiar with. And finally, the power transmitted along a stretched string is 1/2 mu a squared omega squared v, where v is the speed of wave on the string. Alright, let's use these now to solve a few problems. Example 1. One end of a string 6 meter long. The length of the string delta x equal to 6 meter is moved up and down with simple harmonic motion at a frequency of 60 Hz. The wave reaches the other end of the string in 0.5 seconds. What is the wavelength of the wave in the string? We want to find the wavelength. Now, what is the equation which is relevant in here? If you want to find the wavelength, you need the frequency of the wave that is given to us. We also need the wave speed, because the wave equation connects the wave speed, wave frequency, and the wavelength. So, if you want to find the wavelength, I need the frequency and the wave speed. I've got the frequency. Is there any way I can find the wave speed from the given information? Yes. A length 6 meter, the energy of the pulse travels a distance of 6 meter in 0.5 seconds. Distance traveled is given, the time is given, we can calculate the speed. Alright, always start a problem with the given data. Delta x equal to 6 meter, the frequency f equal to 60 hertz, delta t, the time taken by the pulse to reach the other end of the string, is 0.5 seconds. The wave travels the length of the string in 0.5 seconds. Therefore, wave speed v equal to delta x divided by delta t. That is 6 meter divided by 0.5 seconds. That is 12 meter per second is the speed of the wave. Now we have the speed, we have the frequency, we can now find the wavelength. We know v equal to f lambda. Therefore, lambda, the wavelength, is v divided by f. Now, v is 12 meter per second. Frequency is 60 hertz. Therefore, lambda is 0.2 meter. Okay? Another one. Example 2. The wavelength of violet light is 7 times 10 to the negative 7 meter. If the speed of light is 3 times 10 to the 8 meter per second, what is the frequency of violet light? I hope you know by now that the colors that you have in white light, the colors are different because of the frequency and the wavelength. Each color corresponds to a particular wavelength and therefore a particular frequency. Now, what is common to all colors is the speed. All colors travel with the same speed in vacuum, and that speed is 3 times 10 to the power of 8. Speed of light is a constant, and its value is 3 times 10 to the 8 meter per second. Now, the wavelength of violet light is given, the speed we know, therefore we can find the frequency. All we need to do is use the wave equation. So, lambda is 7 times 10 to the negative 7 meter. Speed of the wave is 3 times 10 to the 8 meter per second. And we use the equation v equal to f lambda. I told you this wave equation is equally applicable to mechanical waves and electromagnetic waves. Light is the form of electromagnetic waves. We have v equal to f lambda. We need to find the frequency. Solve for the frequency. F equal to v over lambda. That will be 3 times 10 to the 8 meter per second divided by 7 times 10 to the negative 7 meter, and that is 4.29 times 10 to the 14 hertz is the frequency of violet light. Okay, let's do another one. A steel wire is 7 meter long and has a mass of 100 grams. Now watch the information given here in the first sentence. I have given you the length of the wire. I have given you the mass of the wire. Can you use those two quantities to calculate the mass per unit length? Yes, you can. Alright, it is under a tension of 900 Newton. It is stretched by using a force of 900 Newton. What is the speed of transverse pulse on this wire? So here we are talking about a stretched wire. We need to calculate the speed of transverse waves on that string. Can you recall the equation we developed for the speed of transverse waves on a stretched string? Alright? It is V equal to square root of the tension T divided by mu the mass per unit length. Now what do we have? We have delta X equal to 7 meter. Mass of the string is 0.1 kilogram. Is that right? 100 gram is 0.1 kilogram. And the tension of the string is 900 Newton. Well, If you have delta x, the length, and m, the mass, we can find the mass per unit length. So first we obtain the mass per unit length as mu equal to mass divided by the length. Is that right? Mass per unit length. That will be 0.1 kilogram divided by 7 meter. And what's that equal to? That will be 0.0143 kilogram per meter. That is mu, the mass per unit length. We now have the tension, we have the mass per unit length, therefore speed of transverse wave on the string V equal to square root of T over mu. Let's use those values. T is 900 Newton, mu is 0.0143 kilogram per meter, and calculate that. Now always remember, when you listen to the lectures, especially the problem solving sessions, keep your calculator, piece of paper with you so that you can work along with me. Use your calculator and work it out. And make sure that the answers I have given you are the right ones. Sometimes I make mistakes. Alright, I got it as 251 meter per second as the speed of transverse wave on that string. Okay, let's do another one. Transverse waves travel at 150 meter per second on a wire of length 80 centimeter, that is under a tension of 500 Newton. What is the mass of the wire? So this time we need to find the mass of the wire. Well, look at the data. What do we have? We know the speed, we know the tension. You see, there are three quantities involved there: speed, tension, and mass per unit length. If you know the speed and the tension, we can use those two values to find the mass per unit length. Is that right? And once you know the mass per unit length and the length of the wire, we can calculate the mass of the wire. That is the strategy for the problem. Alright, let's pick our data. The length of the string is 80 centimeter, that is 0.8 meter. The speed of transverse waves in that stretched string is 150 meter per second. The tension is 500 Newton. First we obtain the mass per unit length mu using the equation for wave speed. What is the equation for the speed of transverse waves in a string? It is V equal to square root of T over mu. Can you mentally solve for mu from here? Alright? You can see V squared, if you square both sides. V squared equal to T over mu. Therefore, mu will be T divided by V squared. Is that right? So, V squared equal to T divided by mu. Therefore, mu equal to T divided by V squared. Let's use those values. V is 150, T is 500. That will be 500 Newton divided by 150 meter per second squared, and that is 0.0222 kilogram per meter is the mass per unit length. Alright, if you know the mass per unit length and if you know the length of the string, how will you find its mass? The total mass will be the mass per unit length multiplied by the length. So m equal to the length multiplied by mass per unit length. That will be 0.8 meter multiplied by 0.0222. Make that correction there. You see how I make mistakes? And that should be, I want you to check this result. I'm going to leave it there like this.